Hello good people, I'm going to talk about a few types of reactions. I'm going to start by exploring the relatively simple combination and decomposition reactions. In a combination reaction, two or more reactants combine to give one product. For example, we can have a single carbon atom reacting with molecular oxygen to give carbon dioxide. Note that we are obeying the law of conservation of mass. We have one carbon atom on the left and one carbon atom on the right, two oxygen atoms on the left and two oxygen atoms on the right. Another example would be the reaction of molecular nitrogen with molecular hydrogen to give ammonia. Two reactants have been combined to give a single product. But there is a problem here. The number of atoms on the left does not equal the number of atoms on the right. I have two nitrogen atoms on the left and only one nitrogen atom on the right. So I'm going to place a coefficient of 2. I have two hydrogen atoms on the left and 6 hydrogen atoms on the right. 2 multiplied by H3 will give me 6 hydrogen atoms. In order to make sure that everything is balanced, I'm going to place a 3 in front of H2. Now everything checks out. Finally, I could read this reaction as 1 molecule of nitrogen will react with 3 molecules of hydrogen to give 2 molecules of ammonia. Do not panic. The balancing of reaction equations will be explored later in greater detail. For now, enjoy the ride. Let me have a look at another example of a combination reaction. Potassium will react with molecular fluorine to give potassium fluoride. I have one potassium on the left, one potassium on the right. That is fine. However, I have two fluorines on the left and only one fluorine atom on the right. To make sure that everything is balanced, I'm going to place a coefficient of 2 in front of Kf. Now I have two fluorines on each side. However, I have upset the potassiums. On the right, I have two potassiums. On the left, I only have one. So I'm going to place a coefficient of 2 in front of K as well. And now everything checks out. Enough of combination reactions. What about a decomposition reaction? When it comes to decomposition reactions, one reactant gives two or more products. For example, calcium carbonate will give calcium oxide, also known as lime, and carbon dioxide. This reaction is already balanced, so there is no need to write any coefficients. Let me bring in another example. Here we have sodium azide that will give sodium and molecular nitrogen. Sodium azide is a compound that is used in airbags. When ignited, sodium azide reacts explosively to release nitrogen gas, and it is the nitrogen gas that inflates the airbag. Is this reaction balanced? Yes, the sodiums are fine, one on each side, but the nitrogens are not. We have 3 nitrogens on the left and 2 nitrogen atoms on the right. How do I balance this? I need to use a bit of mathematics, and I know that most of you were looking forward to that. 2 and 3 are common factors of 6. To get to 6 by using 2, I need to multiply it by 3, so that will be my coefficient. Now I have 6 nitrogens on the right-hand side. In order to make sure that I have 6 nitrogens on the left-hand side, the coefficient placed in front of sodium azide will be 2. 2 multiplied by 3 is 6. The nitrogens are balanced, but I also need to balance the sodiums. Right now I have 2 sodiums on the left and only 1 sodium on the right. To fix that, I'm going to place a coefficient of 2. And now everything checks out. Let's look at one more decomposition reaction. Here we have potassium chlorate that gives potassium chloride and molecular oxygen. The reaction is not balanced. The potassiums and the chlorines are fine, but the number of oxygen atoms is not equal on both sides of the equation. And this is similar to the sodium azide situation. 3 and 2 are factors of 6. So to get to 6 by using 2, I need to multiply it by 3. Now I have 6 oxygen atoms on the right. In order to make everything balanced, I'm going to place a 2 in front of potassium chlorate. By balancing the oxygens, I have upset potassium and chlorine. I have 2 potassiums and 2 chlorines on the left, and only one of each on the right. To fix that, I'm also going to place a 2 in front of potassium chloride. And now everything checks out. There is one more type of reaction that I want to talk about, and that is combustion reaction. Combustion reactions are usually very fast and they produce a flame. Right now, I want to focus on the combustion reactions of hydrocarbons and alcohols. Generally speaking, when we burn or combust hydrocarbon in presence of molecular oxygen, we will end up with carbon dioxide and water. If I pick a hydrocarbon such as propane and react it with oxygen, it will give me carbon dioxide and water. Let me quickly balance this chemical reaction equation. On the left, I have 3 carbons. On the right, I have only 1. So I'm going to place a coefficient of 3. The carbons have been balanced. Next, I'm going to look at hydrogens. On the left, I have 8. On the right, I only have 2. If I multiply 2 by 4, I will get to 8 hydrogens. Now I need to balance the oxygens. What is the total number of oxygens on the right-hand side? I have 3 times 2, that is 6, and 4 times 1, that is 4. 6 plus 4 is 10. On the left-hand side, I only have 2. In order to get to 10, I need to multiply it by 5. So that will be my coefficient. And now I could say that 1 molecule of propane will react with 5 molecules of oxygen to give 3 molecules of carbon dioxide and 4 molecules of water. Let me look at combustion reactions of alcohols. In general, if I have an alcohol and I react it with molecular oxygen, I will end up with carbon dioxide and water, same as with hydrocarbons. As an example, I'm going to pick methanol. Unfortunately, the reaction is not balanced. The carbons and oxygens are fine, but the hydrogens are not. There are 4 on the left-hand side and only 2 on the right-hand side. To balance the hydrogens, I'm going to place a 2 in front of H2O. Now the carbons and hydrogens are balanced, but the oxygens are not. There are 4 oxygen atoms on the right-hand side and only 3 on the left-hand side. If I want to end up with 4 oxygens on the left-hand side, I'm going to place a 2 in front of methanol. By doing that, yes, I have balanced the oxygens, but now I have upset the carbons and the hydrogens. To fix the carbons, I'm going to place a 2 in front of carbon dioxide. Now the carbons are fine, but I have messed up both the oxygens and the hydrogens. Let me fix the hydrogens first. There are 8 hydrogens on the left-hand side and only 4 on the right-hand side. To fix that, I'm going to change this coefficient of 2 into a 4. Now the carbons are fine, the hydrogens are fine, but the oxygens are not. On the right-hand side, I have 8 oxygens in total. 2 times O2 will give me 4, and 4 times O1 will give me 4. 4 plus 4 is 8. On the left-hand side, I have 4 oxygen atoms. By placing a coefficient of 3 in front of molecular oxygen, I will have balanced the equation. Once again, do not panic. We will look at balancing of equations in greater detail later. In summary, a combination reaction will have 2 or more reactants that give a single product. A decomposition reaction will have a single reactant that will give 2 or more products. And combustion reactions of hydrocarbons and alcohols will result in carbon dioxide and water. That is all for now, and I will see you on the flip side.